up with gases and PV equals nRT last time. I have a little more to do in that chapter. So geometry with gases. We'll just go through a few of these examples. Here. So number 90 from your book. 2. Liquid plus gas. You got that as a reaction, and you're asked temperature, this, and pressure. Okay, so this is the question. What mass base chose required? So what we'll do here is we're first going to figure out the moles of gas. Yeah, okay. So we're going to use, we have R, we have T, we have pressure, and we're given a volume. We're going to find moles of O2, and then we're going to work backwards to figure out what the mass of O2 is needed. So solving for N, it'll be PV over RT. Divide both sides by RT. You can solve for N. And pressure is volume is 1.85. R is 0.08206. And temperature already in Kelvin for us. So the number of moles of O2 would be 1.85 divided by 0.08206 divided by 315. So 3 significant figures, that's moles of O2. Now that we have that, we can go O2, moles of O2, run out of space. And now we use the mole ratio. 1 mole of O2 to 2 moles of H2O. gas, we need oxygen, there's one of them. Hydrogen, there's two of them. So 18.02 grams per mole for H2O. All right, so we're going to use that. Moles of H2O on the bottom. 1 mole of H2O. 18.02 grams of H2O equals, all right, on this side. But that's going to tell us how many grams of H2O we need to put into here to get 1.85 liters of this gas. Notice these are gases, and that's liquid. You guys follow that? Yeah, just multiplying those together, I get 2.53 grams of H2O. You guys follow that? No questions? So I'll do 90. Getting this right? I want to do the ones that you don't have answers to. So I did 90. So y'all get a lot of numbers. So I'll do 92. This one, the reaction is 4AL solid, 3O2 gas. Measure at, so here's the pressure, and 25 degrees C. So now we're just doing this backwards from the way we did before. Before we found the moles using PV equals nRT, and then we used stoichiometry to find grams. Here we're given grams. We're going to use grams to find moles, and then we'll use PV equals nRT. So we'll find out how many moles of O2 reacts with 53.2 grams of AL. So 53.2 grams AL solid. Aluminum is 26.98 grams per mole. moles of aluminum, 4 moles of aluminum to 3 moles of O2. That'll give us moles of O2. .2 times 3 divided by 26.98 divided by 4. Now you have 1.48 moles of O2. All right, so now we're going to use PV equals 19. All right. And it's asking for what volume, so this is what we're looking for. We have a pressure of 782 millimeters of mercury, and we have temperature of 25 degrees C. There are probably R values that are in millimeters of mercury. I mean, I know there are, but I don't think your book uses them. I think the easiest thing to do to solve a problem like this is to use that same R value, but let's convert the temperature and the pressure into the correct units. Again, I will give you this on a test. Millimeters of mercury, so 760 for 1 atmosphere. I'll have to switch the camera back. So there's your conversion factor. All right, so I got the conversion factor. 1 atmosphere is 760 millimeters of mercury. .782 divided by 760. So what we really have is 1.03 atmospheres. So we will use that for our pressure. So we can use this R value. And then temperature is 25 degrees C plus 273.15. And that'll put us in Kelvin. .298.15. This has nothing after the decimal, so I'll have to cut that part off. 298 K. All right. I have N, because I calculated that at 1.48. And of course, R is just this. It's constant. So now we can solve for the volume. R. And solving for the volume, I'm going to do volume equals nRT divided by P. That's just dividing both sides by P. 1.48, 0.08206, and 298 K. I should be putting units in, but I'm not. 103. feet. That's the answer. That's okay. You guys okay? Oh, well, since I usually give you multiple choice, this is numerically going to be the answer. It is in liters. And yeah, I guess to be formal, you would put 35.1 liters for O2 gas. You wouldn't even put gas with it. I won't get tricky with the label. It's a numerical value, unit, and label, but I'm not going to play games with something like that. You can calculate the 35.1, you should be able to pick the correct answer on the test. That was 90, oh, that was 92. So we'll do 94. And then that leaves you all the odd ones that you can practice. I don't think, I did get a couple more quizzes put together, but I don't think I have one for this. But if you look under quizzes, I have a few more. So I can catch up with that. Okay, so that was 92. And now we're going to do 94. Your atmosphere. 94. Since now I have solid. Gas. 6 of those. Okay. That's a solid. That's milliliters into standard temperature and pressure. Standard pressure equals 1.00 atmospheres. 25 or 20. That standard has changed over the years. We'll see which one this textbook uses. I won't say standard temperature and pressure on the test. I'll just give you a temperature and pressure. For the sake of this exercise, yeah, 93 does it too. Where would we say this? It's either 20 degrees C or 25 degrees C, but of course written in K. I don't know where in this chapter they're reading it. years, standard temperature was 25 degrees C, and then air conditioning was invented, and then it was more typical for room temperature to be 20 degrees C. Now here I am trying to figure out. So some textbooks use the older ones, and some textbooks use the newer ones. I guess I will just take a stab. Let's see what Google says is current. Wikipedia is going to give you the history lesson. 1982.
I bet it's 20 degrees C.
Let's just go with 20 degrees C. I'm just not sure how.
Last week's with the calculator.
No, I'm going to find it. Let's see what your textbook calls standard temperature. I just thought it was chapter that would mention it. Let's just assume it's 20 degrees C. Move on. But I will give you a definitive temperature and pressure test. My education goes back far enough. I still remember seeing standards at 25 degrees. Uh, 298.15. So we'll use 298. I hope that's what you're booked, so you can solve 95 and see the correct answer. Okay, so the hell is that doing? Massive lithium reacts. Okay. So first we're going to find moles. Let's do this first. Let's get our volume in liters. Divide by 1,000. Trying to find N. Then we have R. Okay, so it's N equals EV divided by RT equals N. Pressure, 1 atmosphere, volume 0.0585 liters. R is 0.08206. Temperature 298. 0.0585 divided by 0.08206 divided by 298. So again equals moles of N2. Okay, so now we have the moles of this. 0.0029 moles 1 mole of O2 to 6 moles of lithium. But it's not asking for moles of lithium, it's asking for mass. Lithium 6.94 grams per mole. And that should do it. Oh,
Is it 0.0239 or 207?
oh, did I put an extra 0? Did I? Alright, let's see. 0.0585 divided by 0.08206 divided by 298. No, it's 00239. Did you calculate it and get a different answer? I do it wrong sometimes. Is that why you have? Did you say I had too many zeros here?
Yeah, I don't know.
Let's do it one more time because I do it wrong sometimes. 0585 divided by 0.08206 divided by 298. That's right, there's 2 zeros. So that's 2 zeros. 0.00239 times 6 times 6.94. So I get that many grams of lithium. Stoichiometry with gases. That's a gas, so we can actually use PV equals nRT to calculate moles. You guys okay? What else? Do partial pressure. Exercises 67, 68, 73, and 74. I'll write this little question out. 67. If you read 67, I'll just put the essential information up here. So these are these are mixtures of gases. So 67 says, get a picture of that. No, I don't want to do 67. I want to do 68. So this is So there's a mixture of gas. So that's one piece of information. And it also says we have CO2, and its partial pressure is I'll say pressure T for total pressure. In this one, I'll say partial pressure CO2 is a subscript. Now, I'll tell you what partial pressure is. It's not hard. Also, there's argon in the same chamber. It's O2. There's one more gas, helium. Partial pressure. Okay. It's actually very simple. You have a chamber that's got all four of these gases in it, and the total pressure inside that chamber is 745 millimeters of mercury, whatever the pressure unit is. That means, let me go ahead and do this. 745 minus 112 minus 225 minus 114. What's left is 294. So, of this overall pressure, the CO2 is exerting 112 of it. Argon is exerting 225 of it. O2 is responsible for 114 of these, and helium is responsible for 294 of these. Meaning all of these add up to 745. It's not any harder than that. You guys follow that? So if I wanted to write it in formula, I could say pressure total equals the pressure of CO2 plus the partial pressure argon plus partial pressure O2 plus partial pressure helium. The first question in number 68 says, it gives you all that information, 745 and all of these, and it says, oh, by the way, there's also helium in there. Tell me what the partial pressure of helium is. All I did is take 745 and subtract. That's what was left. So that's how I got the partial pressure of helium. Make sense? Partial pressure sounds complicated, but it's a pretty simple concept. But it asks you the partial pressure of helium, and it says, what is the mass of helium gas? So all of this is only mentioned pressure so far. It's saying, I'll rephrase it, but if these gases are in 12.0 liters, and just walk right over this. Is in the chamber, I'll say chamber. They're all in a gas chamber together. So now we did something very similar to what we were doing. So we found 294 millimeters of mercury. If it's but we're gonna find out how many moles of helium are in there. And we're gonna go 294, the partial pressure. And I'm gonna do, what am I doing wrong? Yeah, 273. It also says, but I'm going to turn this into atmospheres first. 294 divided by 760. So 387 atmospheres. So volume equals 12 liters. Temperature is 293 K. And R and then N is what we're solving for. PV equals nRT. Divide both sides by RT. I get PV equals N. So that's the equation I'll use. Pressure is 0.387 atmospheres. I'll put units in this time. Volume is 12.0 liters. R is 0.08206 liter atmosphere. Kelvin. Temperature 93 K. That's going to give us moles, and then we can find the mass. 0.387 times 12 divided by 0.08206 divided by 293.
It's 270.
Oh, does it say 270? Thank you. It's 273, given in the problem. All right. 0.387 times 12 divided by 0.08206 divided by 273. That many moles of helium. And then we're just going to use helium is 4. Helium is 4.00. Grams of helium. That's the answer. Partial pressure. Also going to do, that was 68, I'll do 74. tell you what mole fraction is next. Mole fraction. Yeah. I'll just do 73. Mole fraction is moles of one component times 100%. If you had a mixture of gases, you got a certain number of moles of one, you got a certain number of moles of another. You take the total moles as your, no, I did that upside down. That's mole fraction. Of all the moles that are there, what's the fraction that just of one of the components? Does that make sense? That's mole fraction. But let me back up and do, it turns out 73 and 74 are kind of different, so let's not do something else I want to get to. A mixture contains 1.05 grams of N2. O2 in a 1.35 liter container at 15 degrees C. Calculate the mole fraction and partial pressure of each component. So we've got this, and we've got this. For that particular okay, the first thing we'll do, we're going to need get those moles, add them together, and that gives us N for the PV equals nRT. So we've got to find the total number of moles first. Grams of N2. N2, there's two of them, 14.01 equals 28.02 grams per mole for N2. So this is how many moles of N2 are there, 1.05 divided by 28.02. Moles of N2. And we've got O2. That's going to be 32. 16 for each oxygen that's there, so 32.02 grams of O2. 1 divided by 32.02. So now that we have both of those, we can add them together. 0.0375 plus 0.0422. So total, I'll say NT total equals 0.0797 moles of gas. Okay, if it's that many moles of gas, then for N2, 0.0375 divided by 0.0797 times 100 mole fraction. Did I say mole fraction? Mole fraction is about 100%. 375 divided by 0.0797. So the mole fraction for much. And that is unitless. And then the mole fraction for O2, 0.0422 over 0.0797 for 22 divided by 0.0797, 0.529. And these should add to 1. 7, 10. Yep. So those add up to 1. So there's the mole fractions. Now it wants the partial pressures. First we have to find the overall pressure, and then we can multiply it by the fraction. You guys with me so far? It's tedious, I know. I'm just going very slow, so it's obvious what I'm doing. Crap. I erased it. What was the total number of moles? Who's taking notes? 0.070797. Is that right? That was our total moles. And I need the pressure. PV equals nRT. Divide both sides by volume. You get pressure equals nRT V. So we've got N is 0.0797. R .206. We're in liters, we're in Kelvin, right? 288. Yeah, it has to be just 288. Nothing after the decimal. These have after the decimal, so those don't count. 288. And the volume, 1.35 liters. So 0.0797 times 0.08206 times 288 divided by 1.35. I get 1.4 that's going to be atmospheres. Okay. Of the 1.40 atmospheres, multiply that by the N2 fraction, 0.471, and then the 1.40 atmospheres. This is for N2, this is for O2, 529. .40 times 0.471. That equals the partial pressure of N2. 0.529 times 1.40. Partial pressure of N2. You guys okay with that?
Multiply it by
We found the mole fractions. And then if you multiply the mole fraction by the overall pressure, that's the partial pressure of that one fraction. You guys follow that? Partial pressures. It is more tedious than it is hard to understand. Maybe it's just me this morning. One other thing. This is a return to 9.4. There's another section in there called I would subtitle it so let me go back. We're going to do a lab that's based on this, so I thought I'd do it more explicitly. By the way, we'll do a lab Monday. So back to this chapter, thermochemistry. I want to do 62, 64. I'm going to do 66 as well. Wafer of pure gold. What am I looking at? 62. Looking at 22. Iron rod in. Initial temperature 22.7 degrees. Final temperature 22.7 and 59.5. What am I missing? Oh. Not this time. All right. Make a diagram. Make a bigger diagram. This is the lab we'll be doing, so it'll be worth a little time. So there's water. So that's an iron rod. This is 100 milliliters of water. 32.5 grams. All right, and its temperature initially, let me read it. Again, this is what we're doing in the lab, so. One more shot at a diagram. Okay, so let's, chunk of iron. There's 32.5 grams of it in there. And its temperature is iron initially. It's in water. 100 milliliters of water. No. Yeah, let me just explain your lab. And I'll save solving those after I explain your lab. No, a better idea. I'll do 66, because this is just like your lab. It'll be worth the explanation once I get to it. Here's what's being described in 66. Okay. Chunk of unknown substance. It's 2.74 grams. initial, comma, unknown. The initial temperature of this unknown chunk is initially at 24.7. The water is at 24.7 degrees C. This is an initial temperature. Okay, good. All right. Initial temperature of this unknown chunk. I heated it up to 72.1 degrees, and I dropped it down in this water. The water was at 24.7 degrees. And I'll say temperature initial. So the initial temperature of this surrounding water, temperature initial water, 24.7 degrees. I dropped this chunk of unknown metal in here, and I heated it to 72.1 degrees, and then dropped it down in this water. So I've got a temperature measuring the water, and I had a way of measuring this temperature when I got it up to temperature. You with me? Diagram this balance. So I've got 15.2 grams of water, 2.74 grams of the unknown. I've got 24.7 degrees C initial temperature of the water, and 72.1 degrees C initial temperature of this unknown metal. And then time goes by, and they come to thermal equilibrium, which basically means they come to the same temperature after a little while. I'm going to call this temperature final equals 26.3 degrees C. And this one's temperature final. So I don't have temperature final of water and temperature final of the unknown. They're the same temperature after a little while. If you just let the heat come out of this hotter thing into the water, and assume it's completely insulated, so heat's not escaping. All the heat that comes out of here is going into the water, and after a while they come to equilibrium, meaning they come to the same temperature. You could picture a thermometer down here, measuring the temperature. That just makes my diagram look ugly. So there's your thermometer. This would be like that. You guys follow the situation I've described? You've got an initial temperature of the unknown. You've got an initial temperature of the water. The final temperature, they're both the same. I guess I could say temperature final of water is 26.3 degrees C. Temperature final of the unknown is also 26.3 degrees C. So you understand the situation I've described? This is what we're going to do in lab. We'll heat something up put it down in a styrofoam cup, and we'd be measuring the temperature. All right, the question is, what is the heat capacity of the unknown metal? This is actually how you can measure the heat capacity. All right. So you answer these two questions. How much heat was lost by the metal, and how much heat was gained by the water? I'm going to write this stuff down here so I have some room. Temperature initial of water equals 27 and 24, 7 degrees C. Mass of water equals 15.2 grams. So we were able to measure the mass of the water and the temperature of the water at the beginning. We were able to measure the mass of the unknown metal and the temperature of the unknown metal at the beginning. We put them together, we leave them, their masses are of course still the same over here. What's changed is the temperature. This one's temperature has gone down to 26.3. The water's temperature has gone up from 24.7 to 26.3. This lost heat, this gained heat. You with me? Let's do, I'm just going to call this Q. Q metal, I'll say QM, and this will be Q of the water. And this is something we've done before, we just haven't used it this way. Real quick, look at the table with heat capacities. And the heat capacity of water is 4.18 joules per gram per degree C. Heat capacity of water is right. So you have everything you need to know how much heat flowed into the water. So it's Q for water is mass of the water, 15.2. The delta T of the water, delta T for the water equals temperature temperature final minus temperature initial, which is, the final temperature was 26.3. Oh, I should put here temperature final water minus temperature initial water. So temperature initial water was 24.7. Temperature final for water was 26.3. So it's 26.3 minus the initial 24.7. So the delta T, 26.3. Final one, yeah. It must be Friday. And so this should come out positive. 1.6 degrees C was the delta T. and then the heat capacity. Running out pretty greasy. So you multiply that out, you get 15.2 times 1.6 times 4.18. The amount of heat that flowed into the water is 101. I guess I have to say 100. That many joules. We've got 3 significant figures there, but it boils down to 2. Yeah, so I'm going to get 2 significant figures, so I guess I have to say 100 joules. You with me so far? Between earlier, when we first started the experiment, to later, 100 joules of water entered, 100 joules of heat entered the water. That's what we found out so far. You with me? Anybody lost? Okay, all of that heat came from the metal. So the amount of heat that left the metal, Q the metal, equals, it's essentially the negative. Yeah, I'll do the negative. It lost heat. So I'll say negative. All right. Now let's just do absolute value. It won't matter. So the heat that left the metal was 100 joules. The amount of heat that entered the water is the same as the amount of the heat that left the metal. I'm probably just over-explaining this. You guys follow me? So that's how much heat left the metal. The amount of heat that entered the water is the amount of heat that left the metal. So this is mass of the metal, delta T for the metal, times the heat capacity of the metal. I'll just see. The mass of the metal was 2.74 grams. The delta T for the metal, delta T metal is temperature initial for the metal, and temperature final for the metal minus temperature initial for the metal. Final for the metal was 26.3. Initial was 72.1. This is going to be negative, but this is what I'm saying. We'll just do absolute value. 26.3 minus 72.1. So this one's delta T is negative 45.8. So that's delta T of the metal. But I'm just going to use the absolute value. 45.8. So we have this, we have this, we have this. The only thing we don't have is the heat capacity of the metal. This is the heat capacity of water. This is the delta T. This is the grams of the water. We calculated that to be 100 joules. That's also how much heat left the metal. So 100 joules, and then the grams of the metal, and the delta T of the metal. Now we can calculate the heat capacity of the unknown metal, which is what we'll be doing. You with me? Did I put you to sleep? So it's 100 divided by 2 point. You want to see the algebra? We've got the Q, we've got mass, we've got delta T, and we've got the heat capacity. These are the things that are known. So I'm going to put the Q for the metal and divide both sides by M, divide both sides by delta T, and that gives me the heat capacity. The Q is in joules, the M is mass is in gram, and the delta T is degrees C, which are the units of heat capacity. So 100 divided by 2.74, and then divided by 45.8. So heat capacity for the metal is 0.797 joules per gram per degree C. That's what we'll be doing in lab. We're literally going to use a styrofoam cup, heat up some metal, take temperatures, etc. You follow that? Really, this question said, this metal sample is suspected of being gold. And then at the end, this says, is it possible this is gold? Well, you know about finding the heat capacity. If you look at this chart, gold is 0.128, so that's not even close. So that's definitely not gold, assuming I did the calculation right. So one little more twist on my question is, could this possibly be gold? 66. That's the one I just did, 66. What is the heat capacity of the unknown substance? That's the main point here. And assuming I calculated it correctly, it could not be gold. All right, you guys good? That's where our lab's going to be Monday. Finding the heat capacity of an unknown. Yep. Okay. We'll stop there.